Good morning, everybody, or good afternoon, wherever you are. And my name is Wolfgang Kinzelbach, and I would like to give the introduction to this webinar series. Now, my contents will be in 4 points. First, I would like to talk about overpumping. What is it and why does it happen? Then the next point is to introduce what we understand under sustainable groundwater management. And then I will go into the example that is our Guantao project in China, and I come to some conclusions. Now, first of all, what does overpumping mean? Now, an aquifer is defined by its water balance, and its water balance is composed of a recharge and of a discharge. Let's look at the example shown here on the screen. This aquifer has recharge by seepage from rainfall. It has discharge by 3 items. First of all, the pumping of groundwater, then some evaporation or evapotranspiration in the place where the groundwater table becomes very shallow, and finally a discharge to a stream or a river. Now, the overall balance of the aquifer is in equilibrium if over a longer period of time the average recharge is equal to the average of all these discharges. Now, the balance changes if either the average recharge or the average discharge are changing. So let's look at the development of this aquifer if, for example, recharge changes. Now, if recharge changes, let's say recharge becomes somewhat smaller, then of course the groundwater table will go down. The declining groundwater table not necessarily means that the aquifer is overpumped. It could be on the way from one equilibrium to another. Like in our example, assume the pumping stays the same, but the recharge reduces somewhat. Then the ground table goes down, and with the decrease of the gradient, less water discharges to the river, and with the going down of the water table, less evaporation happens. And if these two changes just balance out the decrease of the recharge, we get a new equilibrium, and it's not overpumping, although the groundwater table has gone down. Now, what do we mean by overpumping? We mean that if on average recharge becomes smaller than total discharge over a prolonged time, we cannot get to a new equilibrium, and then we talk about overpumping. Now, this overpumping can be caused by decreasing recharge or by increasing discharge, for example, by pumping, or by both combined. Now, how can we see overpumping? Well, if we look at it at a very large level, at a very large scale, let's say the global scale, we can look at the results of the GRACE mission. Now, the GRACE mission is a satellite mission with 2 satellites which measure the gravity field of the Earth. And the gravity field is measured by measuring the distance between the 2 satellites. Actually, it shows differences in gravity field. As the satellites orbit, if they feel a larger gravitational pull, their distance will become smaller. And if they have less gravitational pull, then their distance will become larger. And this distance is measured. It is a signal for the change in gravity. Now, this mission made a very surprising observation, and that is that the gravity field of the Earth changes in time. Now, what is the reason? The only thing which is transported in such large mass that you can see gravitational differences in the distribution of gravity over the Earth is water. So changes in stored water mass were the reason for seeing gravity field changes in time. Before I show you this global picture, I would like to remind you that the resolution is low. So we cannot see whether we locally do overpump an aquifer, but we can only see it for areas which are larger than 150,000 square kilometers. Now, here are the results of the GRACE mission. These are the global changes in mass from 2002 to 2017. And here they are already translated to centimeters of water column change per year. And you see in red areas where the stored water has been reduced, and in blue areas where water storage increased. Now let's go through some of the candidates. Now, of course, Greenland is the red, that means loss of mass, and that is the melting of glaciers. But we are more interested in dry areas. And here we see, for example, California. And in California, the mass reduction is due to drought and overpumping of the aquifers. Then the same here in Texas and the Ogallala aquifer, the same here in Saudi Arabia, where the fossil waters are depleted, and the same in India, where we have a big overpumping of aquifers. And finally, our subject, the North China Plain. And here you see also a red spot. It is an overpumped area, an area where groundwater storage has been decreased. Now, the main cause for overpumping worldwide is agricultural irrigation. And now we look in more detail at the North China Plain. Note that the color code is a bit different here. Here, decrease is in blue tones and increase in yellow or red tones. And here you see again the decrease in water storage in the North China Plain. This is a picture with the change between 2002 to 2013. And the depletion is about 6 to 8 billion cubic meters per year over that period. You also see a slight increase in gravity, increase in water storage. This is the Three Gorges Reservoir. Now, in the North China Plain, of course, we have no glaciers like in the Himalayas. So here it's really due to the change in groundwater storage. We also can see that on the ground. If we look at groundwater observation wells, we see a constant decline since the 1980s of groundwater levels by 20, 30, 40 meters below ground. Now, if we take the results from GRACE, the signal from GRACE in the middle of the North China Plain, and we look at the years 2002 when the mission started, and we include the new data of the follow-up mission to 2020, we can see that we can align the decline with the water level decline, but the decline here is given in millimeters or centimeters of water per year, and we have to take this to calculate what that means for the groundwater table. Now, these 45 centimeters of water column decrease have to be divided by the porosity of the aquifer to give about 15 meters of water table change, and that pretty much agrees with the observed groundwater table change in the aquifer. Now, what is the cause? Is it a decrease in recharge or an increase in pumping? And to see that, we look at data from a typical county in the North China Plain. Here in this graph, you see two curves. You see a blue curve and a gray curve. Now, the blue curve is the development of precipitation. It's not the annual precipitation because that curve would be very noisy. This is a moving average of recharge, a 30-year moving average, and that will smooth the curve and you see the trends. Now, you see that from the 1980s, precipitation decreased and then it picked up again in the after 1995. Now, what happened to the groundwater? That is shown in gray. In gray, you see the decline of the groundwater table, and it declined in parallel to the decrease of precipitation. And then you see that when precipitation starts to increase again, groundwater table is clearly still going down. And that is an evidence that we have a man-made depletion of groundwater in the North China Plain. Now, North China Plain is a very important agricultural region for China. It is the breadbasket, so to speak. 60% of the national output of winter wheat come from this area, and 45% of the national output of maize are produced in this area. And they are produced in a double cropping system. Winter wheat is followed by summer maize. Now, and it is mainly the winter wheat, which is the culprit causing the overpumping. Why? Well, look at the rainfall distribution. You have practically very little or no rainfall in the winter half year, and you have the summer monsoon, which brings the main rainfall. So the summer crop can easily be fed by the rainfall, maybe with some additional irrigation, but we have a large deficit, a water deficit between the crop water requirement and the rainfall in the early months from February to June. And that deficit has to be covered by irrigation. And as there is not much surface water available, it is covered by groundwater. So this is the culprit, the reason for overpumping. Now, why bother? Actually, overpumping contains an inherent mechanism of self-regulation. If the water level in a well declines, then the yield of the well will decrease. And if the water level gets lower than the level of the pump, then of course you get zero yield of this well. At the same time as the water table declines, the energy cost for pumping groundwater up to the ground is increasing. So take these two things together, then the pumping rate has to decrease, and eventually you strike a new balance with recharge, but at a much lower groundwater table. So present food production level is misleading. Lester Brown called this a food bubble. We produce more than we can produce indefinitely. But long before we get to this new equilibrium or to this overpumped, very deep groundwater level, there are already serious consequences of overpumping. And I would like to list them, starting with a groundwater table which is initially high and then declines. The first thing one notices is a reduction in the base flow of streams. If a stream is no longer in contact with the groundwater level, it cannot drain groundwater. It cannot, in low flow times, have a base flow of groundwater. We also will then lack ecological flows in these rivers, and there is a loss of wetlands. The reduction of wetland area in Hebei was about 90% in the last 100 years, and the stream beds today are generally above the groundwater level, so there is zero groundwater base flow. In Northwest China, a consequence of the drawdown of groundwater levels was the die-off of phreatophytic vegetation. That is vegetation like the desert poplar here, which is relying on the groundwater table to get water. Another consequence, which is seen a lot in North China Plain, is the soil subsidence on the cities up to 2.5 meters. And you find crevices in the land, thousands of these crevices, and more than 50 are longer than a kilometer. Near the coast, if the groundwater table gets lower than the seawater level, then of course you get saltwater intrusion. And this has proceeded already about up to 50 kilometers inland here in Hebei. And the final thing, which was mentioned by Manfred in his introduction, is the depletion of storage. The depletion of storage means a loss of resilience against fighting droughts, a loss of resilience against climatic extremes, which are supposedly increasing with climate change. Now, let me come to the definition of sustainable groundwater use. Now, we have best practices, and these best practices consist in these four possible management measures. Number one is pumping should be kept smaller than recharge on average in a region. The second is you should use groundwater conjunctively with surface water. The third one is the groundwater table has to be kept at an ideal level between two red lines. And finally, you can do managed aquifer recharge and water banking. Let me just comment on each of these shortly. We can make an analogy of the aquifer with a bank account. Now, non-sustainable use means that we pay less into our bank account than we take out of it. Then gradually the amount of money in the account will go down, the stored money will go down to zero, and this is not sustainable. Now, sustainable means that what I pay into the account is on average the same as what I take out. not at every moment, but on average over the year. Now, what does the analogy say about conjunctive use? Conjunctive use is like having two accounts. You have a current account for your salaries and you have a savings account. You pay in to the current account, and what you don't need for consumption, you put into the savings account. Now, let's say you get out of a job, there is no income. Then for this period, in the time of crisis, you take money from your savings account, and that is how you get over the crisis. So this is the idea of conjunctive use, where the surface water is the current account and the aquifer is the savings account. Let me look at the red line concept. Here you see two red lines between which the ideal groundwater level should move. There is an upper limit, especially in dry areas, because if you get too close to the surface, you get capillary rise from the groundwater level, from the groundwater table to the soil, and direct evaporation of groundwater, which leaves the soil saline. So to prevent salinization, the groundwater level should be at a safe distance, let's say 3 to 5 meters from the surface. But then there is the lower limit, and the lower limit is first designed to guarantee well yield. If the well yield is too small, then farmers need too long for irrigation and they may not have the time to irrigate all their fields. Now, another reason for having this lower limit is to guarantee a reserve for a designed drought. Let's say we want to get over a drought which lasts 4 years, then we know how much water to leave as a reserve to get over these 4 years of drought. In Northwest China, we have an additional condition for the lower level. That is the lower level to which the trees can reach with their roots. Now, over time, we should manage the groundwater level such that it is between the two lines and doesn't leave that space. Managed aquifer recharge is a practice which is used worldwide. We used infiltration bases in our project area. An infiltration basis is useful whenever there is excess of water. And that happens a lot in North China Plain. In irrigation season, the upstream uses water, so the river does not carry water. But in the off-season, when there is no irrigation upstream, then there may be plenty of water. And this plenty of water you can take out of the river, you can put it in infiltration bases and store it in the underground for irrigation in the next season. Now, this was done here. Of course, this is not a very efficient process, depending on the permeability of the soil. Here, about half of the water filled into this pond was lost by evaporation and half infiltrated and enriched the groundwater. There are better ways of doing these things when you look for places which have a large permeability. And these are, of course, the riverbeds. So here is the example of artificial groundwater recharge in the Fallowing River in Hebei Province. And here, excess water from the north-south water transfer was used, and of upstream reservoirs was used and put into the almost dry riverbed. And here you see that around the river, we had a noticeable increase in groundwater levels. Now, of course, this will only profit people who are close to the river, whereas a discharge basin can be put closer to the respective user. Now, groundwater banking is practiced, for example, in the US and Australia, and they use the aquifer as a reservoir. In times of high water availability, water is stored in the aquifer, and in times of low water availability, it is stored. So in a drought year, you pull down, you sell the water. In water-rich years, you fill up the aquifer again so that you can use this reservoir for storing water. And here you see an example of one of the earliest groundwater banks, that is the Arvin Edison groundwater bank in California. And here you see they store water during this relatively good rains, And then when the drought comes here after 1980, then they sell the water again. They store with big rains and they sell water with low rains. So this is a way of buffering the extremes of climate. Now, to do all these things involved in sustainable aquifer management, you need a management system. And here is the design of a management system, which consists of 3 components. The first component is monitoring. The second component is data bank and decision support. And the third component is implementation of the policy in the field. So the monitoring data, whether it's pumping rates or groundwater levels, are transmitted to the server. The server analyzes these data using models and identifies policy options. Then after choosing the policy option, the policy is implemented in the field. And whether the policy is useful or not, you will see in the next years by monitoring. You go through this cycle once every year. Now let me come to our project site in North China Plain. That is Guantao County. So here is China, here is Hebei Province, and in the south of Hebei Province you have Handan Prefecture, and in Handan Prefecture you have Guantao County. It has the semi-arid climate with the summer monsoon rains and dry the rest of the year. You have supplementary irrigation needed mainly by groundwater, and the irrigated area of the county is 300 square kilometers at a total area of the county of 456 square kilometers. Now let me go through the 3 components one by one. First, the monitoring. Monitored items are the piezometry, that is the groundwater levels, the pumping rates, the land use, and of course, we also collect data on meteorology and hydrology. And all these are important inputs for groundwater modeling. Now, first, I have to tell you something about the aquifer structure. In a simplified picture you see here, there is a shallow aquifer, which is about 90 meters thick. Then there is an aquitard of about 100 meters thick, mainly clay material. And then you have a deep aquifer underneath, which is 200 meters thick. The aquitard separates the 2 aquifers and they hardly have any water exchange. Now, the 2 aquifers are very different. The shallow aquifer is not of drinking water quality. It has a high mineralization of at least 1 gram per liter up to 5 gram per liter. Here you see the salinity distribution of the shallow aquifer, and these dark tones, the very dark ones, 3 to 5 gram per liter, that is even water which cannot be used for irrigation. The recharge of this aquifer is good. It has about 20% of rainfall and about 20% of irrigation water application become, again, groundwater. So about 20% is the recharge rate. Now, the deep aquifer is of drinking water quality. It has less than 1 gram per liter, so it's really very good water. But because of this aquitard, it has in this region locally no recharge. Household and industry use this water from the deep aquifer for drinking water purposes, but it has been replaced because of overpumping by water from the South-North water transfer, not completely, but partially. Agriculture still uses deep aquifer water. And the reason is the salinity of the shallow aquifer. So farmers in these areas, if they want to guarantee their yield, they have either to mix the shallow aquifer water with deep aquifer water, or they have to exclusively use deep aquifer water. Now let's look at groundwater level monitoring. A monitoring system has been built up since 2015 in addition to existing groundwater observation wells. And here you see 3 old and long-term groundwater monitoring wells, which give us a very good picture of what has been happening in the past up to today. And these are new observation wells installed since 2015. We have observation wells both in the shallow and in the deep aquifer. Now here you see the water table behavior since the 1980s. This is the shallow aquifer. In the shallow aquifer, we had this fast decline up to about 2000, and then the much slower decline since then, and very little decline in the years after the start of the project. The data are average of the 3 long-term observation wells you have seen in the picture before. And the rates are here 0.6 meter per year and later 0.10 meter per year of decline. Now, if you look at the deep aquifer, which is shown by the lower curve here, the groundwater table decline is worse. It had a groundwater table decline of 1.6 meters up to about 2000, and then a larger decline of about 2 meters per year since then. You see that the differences in heads between the shallow and the deep aquifer are increasing. Of course, with an increasing head, the pushing force, pushing water from the shallow aquifer to the deep aquifer is increasing, and there is, of course, a risk of pushing saline water from the shallow aquifer through the aquitard to the deep aquifer, spoiling the very beautiful groundwater quality. Now, how about monitoring of pumping? Monitoring of pumping wells is much more difficult than monitoring of groundwater levels. The reason is that there are so many pumping wells. But I want to show you a small example from another project we did in China in the Hebei Basin. And there in Lotachang Irrigation District, we equipped all pumping wells, irrigation pumping wells, by automatic smart meters. A smart meter is a device which you can operate with a swipe card or a stick card. The card contains the amount of water you're allowed to pump. And once you swipe it, the water you pump is subtracted from the card. So that way you can control how much people pump. So for the first time in this region, we know since 2015 how people are pumping during the irrigation season. This application was very successful. It's a modern technique, and one would think maybe that's also something we can do in North China Plain. But in North China Plain, things are much more difficult. Number one, the wells are much smaller. The majority of wells look like this picture on the left, which is a very makeshift kind of pumping. The pump is taken out in winter, it is put back again for the irrigation season. So it is technically and economically very difficult to equip all the wells with smart meters. And that is why in the end, we resorted to a proxy, and that is electricity consumption. Of course, there are also smart meters in North China Plain, but very few compared to the millions of wells which are pumping. Now, this way of using electricity consumption by pumps as a proxy for water use will be introduced in detail by Dr. Wang Lu. So the energy consumption, the electricity consumption is provided by the electricity department, and they can provide it from the county's level to the well scale. And there is a positive development since 2018. There are smart electricity meters installed by the electricity department on single wells, and every day the pumping data are sent by remote transmission to the headquarters. And this system is maintained by the electricity department through the electricity fees. Now, to get from electricity to water volume, you have to have a conversion factor, and this is supplied by pumping tests. So if you do a pumping test for every well, you can say how much electricity at this well corresponds to how much water. And here you see the rough numbers, the averages. Roughly, it's 2.62 cubic meters you get for every kilowatt hour of electricity in the shallow aquifer, and 1.32 cubic meters per kilowatt hour in the deep aquifer. So for the first time now, we know how much a village is using, how much groundwater, in addition to some other water resources, a village is using. So here you see for each village the total volume of water used. And these are the results for 2019, where you see the two sources, groundwater abstraction and surface water which is coming from the canals. This is the same map, but on the level of townships at a lower resolution. Land use monitoring is also a very interesting indicator to show how much water is used. Because the planting area, of course, determines the irrigation needs. What we monitor is the winter wheat area, the summer maize area, and the greenhouse area. Here you see the examples for the year 2019, and the methods will be introduced in detail by Dr. Silvan Ragetli in another talk. Now, winter wheat is the thing we are most interested in because it needs the most groundwater. And winter wheat is relatively easily monitored by remote sensing, because in the season when it grows, in, for example, February, it's the only green thing around, so it can be identified pretty easily. It's more difficult with the maize, because there are other things planted which may look like maize in summer. But in both cases, we combine the optical satellite images with radar images, which show the structure, like a field structure of the grains. And in the combination, we get, at a resolution of 10 meters, pretty good pictures of where is the wheat growing and where is the summer maize growing. Now, also looking at spectral composition of this plastic used in the greenhouses, we can also identify greenhouses. And here you see a zoom into an area here, Shoshansel area, and you see the blue spots. These are all greenhouses. And greenhouses have been increasing in recent years. Now, all these observation data are not observation for the observation's sake, but they are used by models to analyze the situation and to determine action. Now, the box model will determine the demand and supply gap from a water balance over the whole county and make plans for the closure of this gap. The 2D groundwater model allows us to understand the past development of the groundwater level development, and it also allows us to plan the allocation of groundwater and surface water in space over the county. Then we have a real-time version of this model, and the real-time version, I will show you later, is a model which is continuously learning and correcting itself by assimilating new incoming data. It's used to predict groundwater levels, but it also is used to quantify the uncertainty of such predictions. Finally, there is the irrigation calculator, which will be introduced in detail by Dr. Marty. And it allows to plan the irrigation water demand as a function of land use. All these tools are first developed by experts, but they should be used by water managers. So they are all integrated into a decision support platform with an easy to use surface. Let me start with the box model and the water balance. Here you see the balance for the pre-project period from 2007 to 2014. It's 2007 because from that time we have more reliable electricity data, and the units in the graph are millions of cubic meters per year. So you have three items of recharge: the rainfall infiltration, the irrigation backflow, and the recharge from surface water like a river and canals. Now these three add up to the total recharge. And then you have the withdrawal by wells as a discharge. And this is the total withdrawal. And there is the withdrawal from the shallow aquifer and the withdrawal from the deep aquifer. Now we ignore the lateral recharge. It is small against these vertical fluxes which are making up the water balance basically. There is also some use of deep groundwater for domestic and industry applications, which should also be stopped, by the way. So if we look at the gap between what is coming in and what is going out, the gap is about 22 millions per year. The gap is mainly due to the deep aquifer and only to a small extent to the shallow aquifer. So we have a gap between demand and supply of 22 millions, and this gap is of course covered by overpumping the aquifer. Now, how can we close a gap of about 20 million cubic meters per year? There are demand side measures and supply side measures. We can decrease the demand and we can increase the supply. Now the demand side measures, they are all water saving and they are all driven by subsidies. Like for example, subsidy for water saving in the fields, for conservation tillage, for water saving through drip irrigation and sprinklers, and water saving by giving a subsidy for fallowing of winter wheat. Now, if you look at the potential, the only big potential for reducing demand is the fallowing of winter wheat. The potential for water saving is small, not because you cannot save water, but because farmers already save water. Water from the groundwater already costs money, it costs electric energy, so they will not really waste if they can prevent it. Water saving by drip irrigation and sprinklers has a certain potential, but you look at the cost is of course per cubic meter higher. But it's about the same as the cost for the subsidy of saving a cubic meter by fallowing of winter wheat. Now let's look at the supply side. The supply is also a big number here. You could import surface water from the Yellow River and reservoirs, but this is a rather unreliable potential, because when other people, when you are in drought and you need the water, then other people in the upstream also need it. So it will not be as reliable as the groundwater or the gain by fallowing of winter wheat. You also could use more reliable sources, that is the south-north transfer, middle route, or the eastern route, which has to be, or which will be prolonged into Hebei. And this water is, of course, much more expensive than what you see up there. If you would completely fill the gap by fallowing of winter wheat, it would mean that you have to reduce the area of winter wheat in Guantao County by about 30%. Now let's look at the water balance in Guantao in 2019 after 5 years of project, or 4 years of project. And here you see for this particular year, the gap has been reduced. There is not a gap in the shallow aquifer. In the shallow aquifer, the gap is even negative. We have a slight increase in groundwater level. So we gain about 1 million cubic meter per year in storage. So that is negative gap. And then we still have the groundwater pumping, which has been reduced, but is still at 8 million. So the gap is about 7.2 million. Or if we look at the shallow aquifer only, it's on the order of 8 million. I say on the order of 10 million because this has an assumption about the percentage of water which is coming from the deep aquifer, and that is not very exactly known. These data are not communicated. Now, let's go to the 2D groundwater model. Only the shallow aquifer is modeled. The deep aquifer, as I said before, has practically no connection to the shallow aquifer and has no local recharge in Guantao. That means the abstraction from the deep aquifer must be reduced to 0 to be sustainable. And for this, no model is necessary. So let's look at the model of the 2D shallow aquifer. For answering questions of planning groundwater abstraction in space, we can ask this model. For example, what happens in a certain cropping scenario? Where should we put artificial recharge ponds? And we see in this spatial model, of course, distribution, where do we have cones of depression? Where do we have increasing groundwater levels? And then we have a real-time version of this model, and that is the model which is continually improved with new incoming data and which quantifies uncertainty. So let's look at this real-time version. How does it work? The real-time modeling is also called data assimilation because it assimilates incoming new observations to correct the model on the go. Now, conventional modeling, you have a model and you calibrate it well before the time you use it for prediction. And invariably, what happens is that usually the model and the observations are diverging with time. Now, what do you do in the real-time modeling? You do not only model one possible realization of reality. Here you have one reality and you think it's true, but it may not be true. And this discrepancy between model and observation shows that there is some discrepancy between reality and this model. Now, what we do in real-time modeling is we do an ensemble of realizations. We do many models of the aquifer which are equally probable. It could be like that, it could be like that, due to the uncertainty in parameters. And if you do this, you get many predictions. We don't predict over the long time, we predict over a shorter time. And as you predict, you get this divergence of all the different model results from the ensemble. The reality, the average is this blue line here, and the reality may be somewhat different. But what we do now is that we take together the new observation and the model results to filter out from all these possible realizations the ones which are better, which are closer to our observations. We marry the observations with the good realizations, and then we start with that new ensemble, and we go into the future again with a prediction, compare to the observation, take the two together, make a kind of an average of the two, depending on which one is more reliable, and then you get this consequential improvement of the model with time. So you get the improvement of the model, and you get uncertainty estimation of the prediction in the width of this ensemble. So it's a more honest way of saying what we can do than the hubris we usually show when we say this is our model and it is like reality. Now let me just show one page with a few graphic results. So we have the discretization of the aquifer, either in a regular grid or an unstructured grid. This will be shown in detail by Dr. Lining in some of the following talks. We have the infiltration ratio, and we have the specific yield. We have also the hydraulic conductivities. These are the input data, and then you get an output which shows you where you have an excess in groundwater table, where you have a deep cone of depression. And this is exactly the region where you have a lot of greenhouses which cause this cone of depression. Now the model is calibrated, the 2D model, with the past data. That is why we need hopefully a longer time series of past data. And here you see, after an initial adaptation of the model, after forgetting somewhat wrong initial conditions, the model allows to fit the observed heads quite well, not only at this observation well, but at all other observation wells too. And here is the real-time version, where you see not only one line, but many lines, which are the different realizations. And you see the average of these realizations, which is in red. And you see in blue the observations. And you see that also the distance of the ensemble results from each other is getting smaller with time as the model becomes better with new incoming data. The next item, irrigation calculator, to be introduced in detail by Dr. Marty. It takes as input weather or climate, soil data, the crop calendar and the crop area, and with it, it produces as an output the irrigation water demand of a whole region. You just have to put in every crop with the area under the climate, and you get the water demand added up over the year. Here would be a winter crop, a summer crop, and then this scenario which you choose will lead to a certain irrigation water demand. So that's to be shown later. Now, all these things, models, etc., sometimes you think they can only be used by specialists. This is not true. If you provide the model with a front end, which is an easy to use surface, then you can also make these models available to people who are not professionally involved in modeling. And that is what what is our task here. We have water managers in the Department of Water Affairs, and they should use this model to get decision support. So we made a big effort, and this will be shown to you in detail by Dr. Yuli, to integrate all the tools and couple them one to the other in easy to use shell, which is the decision support system for Guantao. Now let's come to policy and policy implementation. There is a possibility of setting quotas and fees. That is a generally used approach all over the world. We can pay subsidies, for example, for not growing winter wheat, the adaptation of the cropping structure as a whole, and we can build awareness. And I show you our efforts in all these fields. Now, policy and economic instruments are listed here. First of all, a personal water right was given to every farmer of about 150 cubic meters per mu. A mu is the Chinese unit for agricultural area, and 15 mu is equal to 1 hectare. So 1 mu is a 15th of a hectare. And just to clarify what kind of agriculture you see in North China Plain, the average area of a family is 5 mu. 5 mu, that means 1/3 of a hectare. So this is really smallholder agriculture. Now, you can use quota or fees for management. Quota, which says you should not step over a certain amount of pumping, and a fee solution that you say you have to pay an additional fee for this water, and the additional fee shows you that water is a rare resource, a scarce resource, and you should manage it wisely. You should use it wisely. Now, in China, they combine the two things, the quota and the fee solution. And it's a 3-tier scheme. First, within your water right, you don't have to pay anything. Only if you overstep a first limit, you have to pay an additional water fee of 0.1 Chinese yuan per cubic meter. And then if you overstep a second limit, this fee is doubled. You have to pay another 0.1 Chinese yuan per cubic meter. Is this a lot, 0.1? Well, the cost of pumping in itself is also about 0.1 Chinese yuan per cubic meter. So the fee will double the cost for the farmer of his water or her water. Now, a red line was set as a lower limit for groundwater level, and the red line for Guantao, guaranteeing the two things which I mentioned before, the yield and the buffer capacity, is at lowest 30 meters below ground. We are not far from this limit. Change in planting structure is another policy, and this includes the subsidy for fallowing of the winter crop, subsidy for planting water-saving crops, or subsidy for planting trees. There's also a subsidy for water-saving equipment and rain-fed cropping. That is, of course, the way out if everything fails. Then people have to go back to rain-fed cropping, which of course is much less, gives much less yield than irrigated agriculture. So here you see the present irrigation water use per mu and the contribution of different water sources to this use. It is here given at a resolution of townships. So there are 8 townships in Guantao, and this is the total. So you see there's quite a difference between townships. The gray part is the surface water, the yellow part is the deep groundwater, and the blue part is the shallow groundwater pumping. So you see people go above the 150 everywhere, but only a few townships go on average above the limit for the first fee, and only 2 go above the limit for the second tier fee of 296 cubic meters per year and mu. So you see, on average, we are not far away from keeping these limits. However, this is on average. There may be farmers here in this township, for example, which exceed it, but others stay below, so this is an average. I have to also mention that the fees and taxes, although they are already calculated, are not yet collected, and this is due to the resistance of the local farmers. They are not rich farmers, and they are fighting not to pay these fees. Now, when you subsidize a farmer for not planting winter wheat, you would like to make sure that he really doesn't plant winter wheat. does not only take the subsidy and then he plants anyway. So this can easily be checked with the land use monitoring described before. It's at 10 by 10 meter resolution, and one mu is maybe 6 of these pixels. So so it's large enough to resolve this planting area. And here you see the picture for 2017 in light green. And if you look by the comparison to 2016, these areas have been winter wheat before and are now fallow in 2016. So they're clearly visible on the remote sensing images. Now, to raise awareness, we did several things. First thing was a board game which we developed together with the School of Arts in Zurich. And this board game was for 4 players, and they play and they see a groundwater level and they pump. And if one player pumps below the red line, then all layers collectively will lose. And this, of course, was a big incentive to keep groundwater level from going below the red line. Now, for this game to be available to more people, we developed out of it an app. And this app you can use with this link, which is given below. It will be introduced in detail by Dr. Liu. And of course, it's a single player, but the influence of other players is imitated by some stochastic events. Now, what we learned in this game playing with the farmers is that if they know where the groundwater level is, they will be quite careful in pumping. So that is why we set up also info boxes showing the groundwater level of an area to the general public so that they can inform themselves how far they are away from the red line. And finally, we did quite a number of workshops with experts and people in China. Let me come to my conclusions. The 2 effective overpumping control measures in Guantao were the fallowing of winter wheat and the increased import of surface water. The shallow aquifer is today practically in balance, but the deep aquifer still requires work. The electricity to pumping volume conversion has shown to be effective and a feasible method for metering of the many small irrigation wells in North China Plain, because all the wells are operated by electricity and electricity is metered. So that allows us to make this method work. The water fees for overstepping quota have been calculated, but are not yet implemented due to resistance by the farmers. The water saving potential is low. Farmers already save water by practicing deficit irrigation. An increase in saving is feasible in the emerging big farms. This is a general tendency in China today that these smallholder farms are aggregated together into big farms, which can operate more economically. They could, for example, practice precision agriculture. And even today, in greenhouses, water can be saved through the use of drip irrigation. The normal greenhouse uses more water than the succession of winter wheat and summer maize in a year. And through the use of drip irrigation, this water use can be effectively reduced. Now, the final solution for the whole of North China Plain, that means also replacing all the deep aquifer water, must combine an adjustment of the cropping system with increased surface water imports. To do everything only through the reduction of winter wheat planting is not possible because it is in contradiction to the Chinese policy of grain safety or food safety, food security, I should say. And that is why we think that a mixture of the 2 approaches will be the final solution to overpumping in the North China Plain. Thank you very much for your attention. I would just mention our sponsors, so the Swiss Agency for Development and Cooperation, the Chinese Ministry of Water Resources, the China Geological Survey, and the Chinese Academy of Sciences. With this, I thank you for your attention.